Our goal today, have I started that yet? No, I haven't. Our goal today in the backboard is to finish section 3.2, which we started on Tuesday. It seems like forever ago. I don't know about you guys, but it does feel. We started it on Tuesday. Our goal is to finish section 3.2, maybe do a few extra examples, and if we have a little bit of extra time, which we might, I'll go ahead and let you guys write down the homework assignment if you have not yet. Some of you might have started it on Tuesday night, some of you might not have. My goal is to also get back for you guys your chapter 2 tests. That way you can start working on corrections, continue working over the weekend. Probably not Monday and Tuesday because most of you are going to be gone, but if you are here, well, in town, might not be in class because, at least for honors pre-calc, everyone will be gone since everyone's an underclassman, aka not a senior. That could give you something to work on as well to get ahead for when you come back. Because these corrections will be due next week, probably next Friday. Next Friday. When corrections will be due. We'll talk about the test when we pass it out. Let's just not talk about it. Okay, so logarithmic functions. Here we go. We talked about, let's see, common log has a base of what? 10. Natural log has a base of? E. E is called, what's his name?
Natural.
The natural number. And what is his value? 2.7. 71828 approximately, and it keeps on going in there. 1828, 1828, 1828. Okay, what else did we talk about? We talked about properties of logs, review properties. Not all of them. We still have a few more properties to talk about, but we did talk about what's going on between logarithmic and exponential. They are inverses of each other, which means they undo each other. So log base a of a to the x, everything's undone but x. A to the power of log base a of x, everything's undone except x. That's the inverse property. One-to-one property, if we can make the logs match, what's that word I was using? With the one-to-one property, with exponential and logs. If we can make them match, what do we do to the base to the log? Ignore. We ignore it. We're not technically canceling it. If we wanted to cancel it, we'd have to do this whole inversely thing about it. Because log base a of a to the x, that cancels, that undoes. But the one-to-one property just says, if they can match, you ignore the logarithms. But what was that last tricky example that you guys got stuck on when you were working together in groups on Tuesday? Which one was trickier, 1 or 2?
One.
Oh, really? The majority of you got stuck on 2. But why? The bases didn't match, so you couldn't use the one-to-one property, and even beyond that, if you tried to raise both sides with the whole inverse, you couldn't even raise both sides as powers of the same base. So since they didn't match, what formula did we use to make them match? Change a base formula. Did you guys actually finish getting this example down? Can you look? Okay, you did? I forgot if we had time or not. So we changed the base to what was over here on the right, a log base 3. How did I go from, oh, I went really fast though. How did I go from log base 3 of 27 to 3 and log base 3 of 9 to 2? That's how I did. I skipped a step. Is anybody able to figure out how I did that?
Can you restate?
Yeah. How did I go from log base 3 of 27 to just 3 and log base 3 of 9 to just 2?
The base number?
The base? No, because the bases are 3s and those aren't both 3s. Ryan, what do you see?
I mean, I just see that 3 to the something power equals 27.
Exactly.
And then 3 to the something power equals 9. So then it would be 3 to the third power equals 27, and then 3 to the 3 squared is 9. So it would be 3 over 2.
Good. So we could have rewritten this as 3 to the third power and 3 squared. And remember, a log is just asking for what power of the base is this number. Well, what power of 3 is 27? 3. Think those two canceled out. They undid each other. Log base 3 of 3 squared. What power of the base 3 is 9? 2. That's how I went ahead and simplified. Now, if you wanted to, we could have also done something like set this equal to x, and 3 to the power of x is 3 to the power of 3, and write it all out. But if you can get the inverse property down, it can save you some work and even help you do some mental math with logarithms, which is kind of crazy because they're kind of complicated. But that's how I got the 3 over the 2. I knew there was something I had to show you guys. I did that really fast on Tuesday because the bell was about to ring. That 3 just got really funky looking, but that's okay. There we go. So you might not need to write that step, but you might want to write that step if you were like, yeah, I didn't really understand how you made that jump. You might want to rewrite it just to help out your ability to look back and still understand what's going on. Everything's funky down here. Sorry, hold on. Nope, that's not what I want. Why is there a G? That became this. Okay, anyway, there we go. But now we're talking about graphs. So, I actually gave you a sketch. Can you just look back in your notes? I think we sketched a logarithm. Where did we sketch a logarithm? Okay, exponential. If you guys found the sketch, it was right at the beginning. Exponential, it grows fast or grows slow?
Fast.
Fast. Exponential growth, growing exponentially. People like to use that like public speakers. Ooh, exponential growth. Like, oh, this is intense, and it's just getting worse. Exponential growth is growing, and it's growing quicker. There's a post-it on my ceiling? What on earth? It was Lee's signature, that's what it is. There's another one up there. Okay, anyway, sorry. Don't know how that happened. Coming back. Exponential growth grows quickly. Logarithmic growth is an inverse. So what we already looked at was if exponential growth has a horizontal asymptote, everything flips with inverses. Logarithms have a vertical asymptote instead. If exponentials have the point of 0, 1, anything to the 0 power is 1. Logarithms have the point of 1, 0. Any log of 1 is 0 because to get 1 you always have to raise to the 0 power. And then last but not least, where exponential swoops up, growing quicker and quicker, logarithm also swoops, but in a concave down fashion where it's actually growing slower and slower and slower by smaller amounts and smaller amounts and smaller amounts. So a logarithm, a lot like an exponential, but flipped across the y equals x because it's an inverse and that's how they behave and how they work. So let's look at this guy. We're going to ask some questions that hopefully you guys are getting more and more and more used to. And the first one is domain. What do you think of with domain? X's or Y's? X, because domain X is range, right? X's. And the questions we ask for what range of, what interval of X's is how far left to how far?
Right.
Okay, so how far right?
Not that far, 0.
Not that far. Stops at 0. Wait, it doesn't stop at 0.
Starts at 0.
Bounded at 0. It can't actually hit 0, right? So yeah, since it keeps going, you need to make it open. There's a vertical asymptote there. It's going to get closer and closer and closer, but never hit. How far right?
All the way.
Positive infinity. So, before we go any further, what do you guys see over here?
There's a problem.
Question. Where in our notes, maybe you might need to use your table of contents, where did we first start talking about the domain problems in functions? It was in chapter 1. We talked about domain with rational functions, but it was way before that. What was it?
1.4.
1.4. Go look at 1.4. In section 1.4, we started making a list of possible domain problems. What are the domain problems that we talked about it? Roots and denominators. So, domain problems, roots and denominators. I'm going to write it over here. Maybe we can leave it up and not erase it. Domain problems. From chapter 1, all the way back in chapter 1, we knew when we have, isn't it even-powered roots, right? Even-powered or even-degree roots. And then we have denominators. But guys, look at the board. What are we going to have to add to that? Logarithmic functions. And I think I barely mentioned them and said, well, there are more domain problems, but we're not talking about those functions yet. Well, guess what? We're talking about one now. So, really quickly, logarithmic functions, it can be any log of u. Now, what's the log that I've written up here on the board?
Log
Common log. But it could be log base 2, log base 7, or ln of x. All of them would have, let's just write log base a. We'll just go ahead and make it general. That way it's talking about any log. Let's review real quick. Some of you just looked at it in your notes. Some of you need to think back. What needs to be true for domain for roots? Greater than or equal to 0, because the square root of 0 is 0. So x is greater than or equal to 0. We're not even doing intervals, we're doing inequalities. Keep it easy. How about denominators? Cannot equal 0. Now look on the board. What's true about logarithms?
can't equal the space.
Can't equal, but also greater than. These kind of, in a sense, a combination of the two up above. No, that's not mathematical at all, but that is just a way of remembering. Even powered roots greater than or equal to 0. Denominators, ooh. Pause. What did I write in the root and in the denominator and in the logarithm?
0 and it should be.
Well, 0 is good, but I wrote x when it should have been u. Why do you think I wrote u instead of x?
Undefined. Unnatural.
Oh, I get it. You're thinking of like the first letter of something. No, not because of the first letter of something. Why did I write a u instead of an x?
The variable.
It's the variable. Abby's like, because you care. Coming back. Is there always just an x in the name?
Oh.
Yeah, maybe it's like a 1 plus x, or maybe it's like a 3x minus 2, or maybe it's like an x squared plus 1. If there's something else in the square root, in the denominator, or in the logarithm, wouldn't you have to start with the argument being greater than or equal to 0, start with the argument being not equal to 0, start with the argument being greater than 0, and then solve for x? So that's why I put the u. It's not always just an x. And sometimes we have to actually solve to get the x part. Okay, coming back here. So our domain problem. So where is there a good place to add this? I don't know. But I would make sure to highlight it, to mark it, to realize now there is a third domain problem we need to be aware and watch out for. Yes, there is one more group. There's one more group of domain problems. And they all come from trig. But we'll get there later. Okay, range. How low, how high? Negative infinity, I agree, it goes down, down, down. Is it going up?
Yes.
Is it going up slowly? Yes, but is it going up? Yes. And here's what's weird about a logarithm. Some of you might think it levels off, like towards a horizontal asymptote, but it doesn't. It keeps growing, and it will keep growing just slower and slower, and it will take forever to get to the same y value as an exponential. In the sense of, it'll take forever to get to high y values. But yes, it will go to infinity. Just very, very, very slowly. But it does keep on going up and up and up. X-intercept. Oh, we already wrote that, right? The 0.10. And the reason for that is what we already wrote down earlier, that log of any base, any legal base, I should say, of 1 is always 0. That's why. Strictly monotonic just means it's only behaving one way as you read it left to right, and it is increasing, but I'm going to put in parentheses very slowly. Well, I just put slowly, but it increases really quickly between 0 and 1. And it slows way down after that. It increases very quickly for fractions, but it increases, yeah, I could say that, but it increases much slower for any number greater than 1. Vertical asymptote is at x equals 0. And for every point on its domain, it is continuous. Smooth curve, no jumps, no breaks, no holes inside the function. inside its domain. All right, this is the parent function, right? In a sense, I didn't really make a base, but we are going to talk about what happens when things change, when there's addition, when there's subtraction, when there's multiplication, when negatives come in, and when the bases change. What do we call that just word that covers all the different ways of changing the function up? Good. Let's talk about it. Transformation. Transformations. The same way that we can transform exponential functions, we can also transform logarithmic functions. The same way we can transform exponential functions, we can transform logarithmic. P.S. Super random. If you're really interested in going on a mission trip this summer, we had our meeting yesterday, but everybody was busy, and PSAT people didn't get reminded. There is a list on the back desk. I have one, Senior Bratche has one, and Mrs. Cameron has one. If you are interested, you can throw down your name, number, email, and there's a little half sheet of talking about each of the 3 trips. You can put down which trip or trips you might be interested in. Just might. Just saying you're interested. I just saw that, so little plug for it out there. Okay. Maybe you guys are pros by now. What's going on with B? Adding on the outside. Vertical translation, or we could shorten it shift, right? Vertical shift. Vertical translation or vertical shift. We'll get back to A in a second. He's the base, and we'll get back to him in a second. How about C? Horizontal shift, because it's a subtraction. A is the base. As the base increases, what was going on as the base increased for exponential? Do you remember? When it changed from like 2 to the x to 5 to the x to 10 to the x, what would happen to that curve?
You get steeper.
Steeper. Right, because 2 to the 10 is a lot smaller than 5 to the 10, a lot smaller than 10 to the 10. So at one x value, one's going to be here, the other one's going to be way up here, the other one's going to be way up there. So it's getting steeper, it's coming in. So if exponentially, just think about this, don't have to write it in your notes. Exponentially, if the curve gets steeper, oh, they all should hit the same point, I apologize. They all have the same y-intercept. Okay. If it's getting steeper, what's going to happen with the inverse of each of those?
Make it flatter.
Exactly. So, what should we say about the base? As the base increases, we can not leave enough space here. The curve, shrinks, vertically flattens, however you want to talk about it. It's going to get flatter. It's not going to get flat by any means, but it's going to be flattened a little bit. Or you could think of vertical shrink in a sense. Vertical shrink in a sense. To be honest, kiddos, going into that blank, I'm just being real, I had no idea what it was, and I was like, hey, let's graph the exponential and figure it out. So thanks for helping me do that. Okay, coming back. Yeah.
There it goes.
Oh.
Where is it?
Don't get lost. Leave your phone on my back desk. Okay. Reflections. Kiddos, how do we get reflections? How do we flip stuff? By multiplying by a negative. So if we're trying to go across the x-axis, I'm just making you practice. Is that a horizontal or a vertical? Think the x. Think flipping around the x. It's an up, down. It's a vertical. I know it's weird. The x is horizontal. That's true. But the flip over, if you were to fold down, aren't you flipping vertically? Right? So if it's a vertical flip, if it's across the x-axis, Where are we multiplying by a negative? Outside. Good. So in some senses, depending on the equation, we are going to need to have some sort of negative outside the log. Let's put it like that. It could also be, depending on the order that you do it, a negative outside like the entire thing. But either way, that negative would still come in and would flip. Across the y-axis, remember, you can always think of it. Graphing the y, flipping across the y, folding on the y. What kind of flip would that be? Horizontal. Do the struggle. It's a Thursday. It's almost Friday. You guys are hanging in there.
Barely.
Who fell asleep during the PSAT yesterday?
I died.
Who did it on purpose? I heard there were a couple accidental ones. Horizontal flip. Where's the negative going to go? Inside. So we're going to have log base A of, yeah, some sort of negative x, or if it's transformed, it could be like a log base A of a negative, ooh, that would be gross. Well, somehow there has to be a negative inside the argument with the x value. Does that make sense? Seems so easy, I'll take it. Not sure that's what you said, though. All right, we ready? What are we missing? Dilations. We're missing dilations. If there was like a 4 on the outside, then yes, there would be a vertical stretch. If there was a 2 on the inside, 2x, it would be a horizontal shrink by a factor of 1/2. Okay. We didn't write down dilations. They don't happen super often. Kiddos, if you need to, well, I'll help you with F, and then you guys are going to try G and H. Someone tell me something about F before it's transformed. What's something that we know about that function that I can graph? The base is 2. What's something I can graph? The x-intercept, I know it has to hit at the point 1, 0. Because every log that's non-transformed, every parent function hits at 1, 0. Because what power of 2 would be 1? The 0 power. There's one other thing I should be able to graph right away. Vertical asymptote is at. Now, that technically was, we wrote that down just a second ago on the parent function, because some of you are still getting used to logarithms. But any non-transformed log, aka no translations or shifts or stretches, is going to have an x-intercept at 1, 0 and a vertical asymptote. Now, how do we swoop it? Well, if only we could get one more point. Is there anything else easy for a log besides when does the base equal 1, 0? What if x was 2? What power of 2 is 2? If this was log base 3, I would use 3 instead. If it was log base 4, I'd use 4 instead. But whenever you have the base and the argument match, the answer will always be 1. So you can find the point pretty easily. Or another point pretty easily. By thinking of, we'll just take the base, and that's going to be when the height is 1. You might even want to go back to the parent function for just a second and say, oh, okay, so not only do I know the point 1, 0, but I also know when y is 1, x is a. Maybe that could help a little bit. So if it was log base 3, this would be 3, 1. If this was log base 7, it'd be 7, 1, which would be way over here somewhere. But that would also make it flatter, which works with what we said about the bases. Okay, now what? There it is. See it? So you guys, take that parent function. You are allowed to collaborate in your groups. I want you to think about, with words, what transformations are happening in G and then in H, and then try to graph it. Ready? Set? Go. I'm here for advice, but not for answers.
You're just gonna go up to you. You're gonna go up 2, and you're gonna go right 1. So you're gonna go.
Oh, because the plus 2
So that's gonna be. So there's a point at 2.
Does it always hit 1-0?
Yeah, it always is.
Still have
Just make it right.
0? What does that mean?
Like,
Well, I don't think it ever touches 0. I think it stays like right next to the entire time. It gets closer, closer, closer. It gets so small.
I'm gonna call random names, make sure you collaborate with your group, whoever you are, whether you're the one speaking or the one just listening. Maybe I'll try to think different.
Yeah, that's why I asked.
Oh, unless it's.
It's gonna be 1 down.
No,
We're gonna always hit 1-0.
this is a positive,
Unless you.
Unless it's been
and it's gonna be
shifted.
a reflection.
Does that make sense? If it's shifted, then all that. But if it's just reflected or dilated.
So we just, it's down below. Because it's 1, so it's positive, so it's gonna be
How many groups are done? Raise your hand, go fast. Everybody's on the same page.
I think it's
No, plus that.
Yeah.
Because it's still.
Yes, if someone has an updated calculator, aka not a yellow button, I guess you could check to make sure you're right. You're checking, not solving.
Well, I mean, that's the SAT.
Okay. Oh, so one's gonna be over class.
Or not math.
For all sides, like,
We were scored all over.
That's for the first
That's
one.
why George had
The first one was 18%. Second one was 7%.
Those were a little.
Like, she'll take the bill thing fine.
That was a question.
That was
That was a question.
Hey, learn how to teach your works.
Well, last after.
Yeah.
So, the big bracket has a domain of 0 to infinity. Your vertical symptom is 0.
And like they had the.
But I didn't know that.
Like with the fractions.
Because we used the common.
5, 4, 1. You ready? Woo! Okay, I'm just looking around because I don't remember who called it last time. I'm pretending. Alright. Rebecca, how would you verbalize what changed in G?
It went 2 up and 1 right.
Too close. Right?
And 1 right, sorry.
Got it. No, you got it. Shift up 2 and right 1. So therefore, Jonathan, how did you take the parent function and move accordingly? What did you choose to move?
For g of x,
Yeah.
I took log base 2 of x, shifted it right.
So what did you shift though on this graph? Points?
Yeah.
Okay, so you shifted right 1 and up 2-ish, right 1, up 2. Okay, right 1, up 2. Is that all you did? Who can add? I'm just gonna get volunteer. Who can add one other thing they should have done? They should have shifted besides the points. Ryan.
Asymptote.
Yes. Where is the asymptote shift? Right 1, not 2. Who cares about the up, right?
It's literally right there.
Now can you go ahead and say, oh, I'm pretty sure I know not only how it's switched to the right, but also where it's bound or shifted to the left. Okay, good. H. Carl, what did your group say as far as the wording as to how H changed? Okay, good. Was there anything else? Okay, you did get the shift up 1. That's good, but there is one more thing. Oh, we're doing volunteers. Abby, go ahead.
Reflection.
Okay, what kind of reflection? It's from the negative. Oh, reflection in? Yeah. You can say it's super snazzy. Reflection in. Oh, did you say that? Oh, you said X. Abby. Oh, you just said X, okay. It is a reflection in the x-axis. I was thinking maybe you had it. What's an easier way of saying reflection in the x-axis?
Across the x-axis.
Okay, across, that'd be what kind of flip? Vertical. So you could just say a vertical flip. Right? Vertical flip. Okay, so then, Thomas, how'd you graph it?
So just shifted everything 1.
Okay, so each of the points? So up 1. Up 1. Then just swoop it?
From the flip.
Ah, the flip. Okay, so how do I do that?
Flip the first division.
Okay. So let's pause with the shifting. If it's all simplified, we can do it in order as PEMDAS and say, okay, the multiplication goes first and then the addition in a sense. So the negative goes first. So I would flip first of all. But does this one flip?
No.
Oh, okay, so he stays and then I shift up 1, right? This one needs to flip and then shift up 1. There we go. Does the vertical asymptote flip and shift up 1?
Confusing until you look at it.
So what's going on? It's swooping. Yeah. You guys get it? Questions? Why was it a reflection or a vertical flip? Because the negative was on the outside of the function. And since it's already simplified, I can go ahead and reflect and then shift. This one, they're both just shifting, so I don't have to worry about the order. Okay, nicely done. Let's keep going. Wait a minute, pause. You might not need to write this whole page, because what is this entire page saying? They're inverses, we already wrote that. But what does that mean? Reflect across the y equals x line, and the x's and y's, the ordered pairs switch. Write what you need. It's just some graphical? Some reminders about the graphs of the functions based on the fact that they are inverses. The end. Okay. Good question. Let me see. Ooh. We have one fun one to do. Oh, party leaders.
He's got this.
Funny thing is, when you say Jello, I think of a person. That's what they call Alexander. And Jackie. I know, I figured. But I was just letting you know not to, but that's okay. I don't really like Jello, to be honest.
What?
I like these.
What is
Like if it's really cold and it's a hot day and it's just sitting there, and I don't have to use my fingers, then maybe. But otherwise. It just makes it 7 up, maybe. Maybe 7 up.
Like Jello waters.
Jello's not about the flavor,
I
it's about
love chicken food.
Chicken on the plate, watching
All like not even couple, just put chicken.
It's
massive
massive
slices.
stuff for putting it in.
I make like a 7 layer of Jello. Oh, the bottom layer, and then you put like this.
Yeah.
Then you put colors.
Oh, let's see what the fun stuff in it. Okay, well, that's different.
That's some experience.
I had some bad experiences with like the
I hate pudding.
family big dinners and like the Jello because it's
Jello's not a meal, it's a way of life.
like canned fruit and just.
What?
That's like childhood with the
But Colby, I'm not saying you're stuck. Now that we've recorded our distraction, let's go.
You need a test.
Alright, here we go.
No, I'm not talking about that. Those are disgusting.
Last problem. So easy, it's hard. Maybe it's so easy, it's easy. What if they say to evaluate? Who already has an answer? Don't shout it. Just good. We'll give them a second. If you're plugging in your calculator, lame sauce. That's no fun. Don't do that. This should be by hand. This should be mental math. Lame sauce. It is sauce that is lame.
They said plain sauce.
Lame sauce.
Plain sauce. I'm like this.
Plain yogurt, maybe? Is that what plain sauce would be?
What does plain yogurt taste like?
Tester.
I thought plain yogurt was like.
You need a test. I can.
We have time. Okay. Thanks for stressing though. What do you do when you evaluate? Plug it in. So y equals ln of who?
E.
To the. Why did I say mental math? This is hard. It's an ln, it's an e, it's a -4. Say what?
Harder than I
How many of you guys caught? Don't say anything. Have an answer in your head. Okay, better than it was before. The rest of you guys, come on. Who is ln? Don't answer the final answer, but who is ln? Log base e. Pause. Who has an answer in their head now? We lost him. Pause. Go look at your properties. Look at the inverse property of logarithms. When you have a log base a of a to the power of x. When you have a log base a of a to the power of x.
Equals X.
No hands go up.
Who is x? Who has an answer now in their head? Shout it out if you think you know it. As easy as that. Because when you have ln of e, it's log base e of e. They undo each other in a sense. They cancel each other out, and all you have left is the power. Yikes. We're going to work on whole mental math and getting used to log things tonight. I'm going to pass out your test as you guys write down the homework. I was going to do it anyway.
Can you help us solve like this one?
Hey, we got to take a test today and look at the videos of your review night action.
I have one problem. I don't have Why are we so sensitive about Jello? Is Jello a dessert?
Good question. I would say yes because almost all Jello has sugar. Okay, I'm going to pass out my test. Your test that you took with the score. The score is just a strict how many points you missed, and I tried to be as nice on partial credit as I could. I really did. The multiple choice were 4 points each. The long answer were 8 points each, which is pretty normal. Long answer is usually about double with the multiple choice. And it was out of 100. So you can go ahead and check if you had any 0.5s. I should have rounded your score up. You can double check that as well. We will talk about everything else once you get it. But if you have not yet written down section 3.2, you should be in your homework spirals writing the assignment down so that you can make sure you have it. So I'm assuming you already started your homework because you're not writing it down. If so, get out your spirals. Don't be posers, be real, get it down. It'll save you time later. All right. So in no particular order whatsoever. P.S. Those who did well did really, really well. And those who didn't do well didn't do well. Okay, so. I don't mean Jacob, Ryan, Rebecca, Janelle, sorry, Ryan,
It's always.
I know. Andrew. Thomas.
Gosh, I was expecting. This is.
Victor. Jack. Kobe.
Oh my god!
Listen. Ryan. Oh my gosh, Ryan! What? Okay, I used to. Alright. The bonus was worth, I think, +4, the same amount as the multiple choice, but you would have had to get the correct answer and the correct notation to get all 4 points. Some of you wanted the wrong answer, you just didn't get it, and that took off a good chunk of points, and that was a bummer. Some of you missed a lot of little things, and that added up, and it was rough. Some of you had whole concepts or whole sections that you just weren't ready on, and it just messed you up because I tested on every single section. Some of you, well, did quite well. We had a 102, we had a 99, we had some 97s, we had, I think, another 99. Now, but we also had the other end as well. Kiddos, you need to think about what went wrong, and we're going to do that with the correction paper. If you want to, go ahead and count up and see if you need another correction paper. Grab one on the way out of the room if you need to. You can always split those corrections in half. But since, listen carefully, even though we did have some really good ones, we had some really high ones, we did have the other end of the spectrum as well for different reasons, I believe. Many different reasons. So these corrections will get points back, but it's only going to be a third this time. It's only going to be a third this time. Those of you guys that had over 100, your corrections will count as the homework assignment as always, but you can't get points added above 100. If anyone below 100, you can get points added. Even if it's a 99 to a 99.3. It is what it is. All right, cool kids. You have these corrections due. I'm going to write on the backboard next Friday. If you want to write that down somewhere, that's a great thing to remember. Otherwise, your homework is due tomorrow. Chapter, this is chapter 2.
I literally
A 104 was possible, but I don't think anyone got one. I think a 102 was our highest this time. Everybody missed something. Yes, one more thing, time out. One of the hugest topics of this chapter was factoring. One of the biggest topics was factoring. That will follow you in math for a long time. So please, focus on these corrections, come in and get help, work together on it, and remember, you can get tutoring hours if you are struggling, aka if your grade on this test is like a C or below. You can have someone work with you on corrections. They can get tutoring hours if they got like an A, and you can get tutoring hours for being helped. Sometimes that is an option. Cool? Being helped? Because if they need help on their corrections, and I think on the green sheet, doesn't it say if you're struggling in even the class that you're in, someone who's in the class can help you? Yeah, just reminding you. Just reminding you. All right.
I just did that.